Now we have talked a lot about the different parameters that characterize the kinematics of a particle. We've talked about the speed, the acceleration, and the displacement, and we've described them in detail. I want you to remember that whatever we've said before is also applicable for a two-dimensional analysis, and here we're actually focusing on a two-dimensional analysis when we're dealing with the curvilinear motion. So a couple of notes about the curvilinear motion. Basically, when working with this type of motion, we are dealing with 2D and 3D frameworks. So the particle is now capable of moving in a three-dimensional or two-dimensional space. And since we're now moving in a two-dimensional or three-dimensional space, the direction is now of interest. So we're interested in knowing exactly the direction of motion. Remember, when we were dealing with a one-dimensional space, there was no interest in knowing the direction since the particle is forced to move along this certain line. So it cannot take any angle. But now that we're dealing with 2D and 3D frameworks, the direction is now important for us. So as we have described before, the velocity, the acceleration, and the displacement, we can do that as well here. The same equations are applicable here, but remember that now we're forced to work in terms of vectors. And so one can write that the average velocity in a 2D or 3D framework as a vector is equal to delta r as a vector divided by delta t. Similarly, taking the limit as delta t goes to 0 to get the instantaneous velocity, one has that dr as a vector divided by dt is equal to v as a vector. Now noticing that delta r tends to delta s as delta t tends to 0, as you can see on the image on the right, then the speed is defined as v is equal to ds over dt. So we're able to replace dr by ds, which is now a scalar. So remember, speed is a scalar value, while velocity is a vector value. Now, why are we actually saying that delta r tends to delta s? Looking at the graph, you know that delta s is the chord. And so as the distance gets smaller and smaller between the two different points, this delta r, which is the change in the position, gets closer to the delta s. And we can simply replace one with the other. Now, similarly for acceleration, the vector a average, which is the average acceleration, is equal to the change in velocity, delta v, divided by delta t. Again, we're working with vectors here. By taking the limit as delta t goes to 0, one has the instantaneous acceleration, a, is equal to dv over dt as vectors, and then doing the replacement again, one has that a is equal to d2r divided by dt2. Now notice that the vector is only valid for the parameters such as velocity, displacement, position, and acceleration, and not for time. So you should never put a vector on top of dt. Okay, so far we've talked about a rectilinear motion, which is a one-dimensional motion, and discussed briefly the curvilinear motion, which is in 2D or even 3D. Now it is of interest to tackle the different representations one can make use of to solve problems that are either 2D or three-dimensional. The very first representation assume rectangular components, and by rectangular components we're actually talking about a Cartesian frame of reference. So we use x, y, and z components. So if one needs to represent the position of a particle in a Cartesian reference frame, one has that RT as a vector is equal to the sum of the different unit vectors that form the Cartesian space. So we have xi plus yj plus zk. And by now you should already be familiar with this sort of representation, since it's more of the traditional representation for 2D or 3D spaces. Remember, I, G, and K are unit vectors, and when we're talking about a unit vector, we know that the magnitude is equal to 1. So the magnitude of the vector I, J, and K do not affect the final position of the object. It's basically the components x, y, and z that dictate the position of the object. Now, if we want to know the magnitude of the position, we can simply take the square root of the different components. So r is equal to the square root of x squared plus y squared plus z squared. And similarly, if we want to find the unit vector in the direction of r, that's the vector that points in the direction of the position and has a magnitude of 1, we can simply do that by dividing the vector itself, r as a vector, by the magnitude of r. So when we do that, we actually normalize the vector r and end up with a unit vector. Now if we take the derivative of the expression of the position, rt, we know that v as a vector is equal to dr over dt. And in order to take the derivative, one needs to take the derivative component by component. So we derive x with respect to time, then y with respect to time, and finally z with respect to time. And so we end up with v is equal to vxi plus vyj plus vzk, where vx is equal to dx over dt equal to x dot. Remember, whenever we add a dot on top of a variable, it means that we're talking about the derivative of that variable with respect to time. A single dot means the first derivative, two dots means the second derivative, and so on and so forth. Also, vy is equal to dy over dt is equal to y dot, and the same applies as well for vz. Now, if we want to talk about the magnitude of v, we can simply take the square root again, as we did before, and the unit vector of v is defined as the vector v divided by its magnitude. Similarly, we can do the same thing for the acceleration. So let us take the derivative of the velocity. So a is equal to dv over dt. And so one can write that axi plus ayj plus azk is equal to a, where ax is equal to x double dot, second derivative, ay is equal to y double dot, and az is equal to z double dot. Again, remember, a is also equal to the square root in magnitude to the square root of ax squared plus ay squared plus az squared. So this slide nicely summarizes how to deal with the rectangular components and how one can derive values for the position, the velocity, and the acceleration in a Cartesian frame of reference. Now let us look at a particular application for the rectangular components, and that's the motion of a projectile. So what does that mean exactly? So in the motion of a projectile, the only force acting on an object, assuming no air resistance, is gravity, or the weight of the object itself. So you can imagine holding a ball and just letting this ball go. And when the ball falls onto the ground, as it falls onto the ground, it is only subject to the gravity or to the weight of the ball itself. And so here we're talking about the motion of a projectile. This also applies to whenever you're holding an object in your hand and you just throw it away, then it will follow the motion of a projectile as it is only subject to gravity or its own weight. And so how can we derive the equations of motion for this scenario? The steps are relatively easy. We need to work each component on its own, the x, y, and z component. Now if we're dealing with a two-dimensional problem, we can simply make use of x and y components and discard the z component. Then we need to derive the terms to get a and v by simply making use of the fundamental equations of motion. Then finally we can add up the different components vectorially to get the final answer. So let us look at the solution. So we know from the previous analysis when we've tackled the case of a constant acceleration problem that v is equal to v0 plus act and that s is equal to s0 plus v0t plus half act squared. So these two equations have already been derived before. Now, following the steps, we know that we need to work out each component on its own. So let us start with x. We know that the only acceleration in the case of a projectile is gravity. So we know that AC is equal to minus 9.81 and it is always directed downwards. One can say that ACX is then equal to 0 and ACY is equal to minus 9.81. So since ACX is equal to 0, when we integrate or when we replace in one of these equations, we get Vx is equal to V0x. Notice that the ACT term cancels out because of AX equals to 0. Similarly, replacing AX equals to 0 in the second expression, one has Sx is equal to S0x plus V0x t. And notice here again, the third term cancels out since the acceleration is 0 in the x direction. Now doing the same thing for the y-axis, notice here that we do have an acceleration, so technically no term should cancel out in the two equations. So we have Vy is equal to V0y minus 9.81 t, and Sy is equal to Sy0 plus V0yt minus half 9.81 t squared. Notice again here we replace the plus with a minus since the acceleration is equal to minus 9.81. Now it is useful to know the number of independent equations we actually have in the case of the motion of a projectile. Remember, we've said that we have three fundamental equations of motion, but only two of them are independent. And so now looking at the different equations we have, we've made use of three equations of motion, or two equations of motion, for each of the components, x and y. But let us look now at the useful equations we have now at hand. So we take out any equation that only deals with constant, like ax equals to 0 and vx equals to v0x, as they both do not give us any insight or do not help us solve for any unknown. And so by doing that, we're left with only three equations. Sx is equal to S0x plus V0xt, Vy is equal to V0y minus 9.81t, and Sy is equal to Sy0 plus V0yt minus half 9.81t squared. So these three equations are the independent equations one can use to solve a problem involving the motion of a projectile. So one can say that any problem related to the motion of a projectile has to deal with three or less number of unknowns, because you only have three independent equations to solve. Now you'll understand why I've talked about that right now when we start solving problems related to the motion of a projectile.